Hello, welcome to Crankshaft, a group presentation on the module Crankshaft. My name is Jacob Foster.
And I'm Luke Foster, and let's watch a YouTube video on how crankshafts work.
Yes, we're going to watch a crankshaft in action. Truly mesmerizing. A crankshaft is a tool that lets you convert the lateral movement of a piston to rotational movement. The connecting rod there that moves off of the piston rotates the crankshaft. We created mathematical models to talk about how crankshafts work. And we're going to answer the module questions that are based on the models that we built. Take it away, Luke.
So for the first question, we're asked to suppose that an automobile is going at a constant 60 miles per hour, which results in the crankshaft rotating at a constant rate of 3,000 rotations per minute. If the radius of the crankshaft is 1 inch and the length of the connecting rods are 4 inches, the piston's maximum velocity would be 26.90314,984 feet per second, and the minimum velocity of the piston would be 0.06168504,009 feet per second. We found that the crankshaft completes a rotation every 0.00. The crankshaft completes rotation every 0.02 seconds. Ugh. We also found that with the same system, we found that the maximum acceleration of this piston would be 10,280.782543 feet per second squared, and the minimum acceleration of the piston would be 18.625,42343 feet per second squared. In graphing the function of the height of the piston over time, it shows a almost distinctly sinusoidal wave within limitations of 5 inches and 3 inches. However, we cannot call this a sinusoidal function because the cosine at the beginning here would be a constant, and this cosine cannot be a constant because it is variable and thus cannot be expressed in terms of sine. Take it over, Jacob.
You got it. I've pinned only my video. This is my show now. Okay. The next question in the module regards changing the length of the connecting rod to see how that impacts the function of the system. It's important to talk about right now the maximum acceleration of the piston at any given time is a good way of tracking how much fuel is necessary, because the fuel is what lets you accelerate the piston. So if maximum piston acceleration is smaller, you're going to use less fuel. But often when we've been messing around with this, we found that changes that are made that reduce maximum acceleration also reduce maximum velocity. In the case of lengthening the rod, that is not quite true. The reduction in velocity is smaller than the reduction in maximum acceleration. However, maximum acceleration reduction has diminishing returns as you lengthen the rod. So while it's a overall gain for fuel efficiency, the longer you have the connecting rod, eventually other considerations will have to stop the lengthening of the rod. That's why we settled on about 12 inches as probably the optimal length for the connecting rod, because after that, the returns of the decrease in maximum acceleration begin to fall quite low. Some other considerations for lengthening the rod are the weight of the piston and the rod. As the rod gets heavier from being longer, um, you're going to need more force to move it, which will actually require more fuel. The module didn't ask us to map that out, but you would have to consider that before making any final decision on rod length. The amount of space available in the engine apparatus is also going to limit your rod, because theoretically a 100-foot long rod is more fuel efficient than a 12-foot long rod, but you would need a massive engine to make that happen. And unless you're using something like this to operate a sawmill, you will run out of room fairly quickly. We're talking about a vehicle, so that's probably the case. Let me check, make sure I didn't miss anything. Okay, yeah, that's everything for question 3. So let's move on. Oh. What if we doubled the radius of the crankshaft? What we found when we did that was we doubled the velocity, and you can find this if you modify the Excel file that will be attached with this presentation. The maximum velocity doubles, which means that the amount of force, the amount of power that the piston is able to generate has increased. And that's going to be useful for doing more work, like generating movement against resistance and moving heavier weights, heavier loads. However, maximum acceleration quadruples when you double the radius. So it is 4 times, it consumes 4 times as much fuel and can do twice the amount of work. So that's the trade-off that you have to make with increasing the radius of the rod. So a larger radius then, because it allows for more force but uses more fuel, is probably going to be more useful in a large work vehicle than it is in a smaller vehicle more focused on fuel efficiency and speed. A race car, for example, needs to be fairly light, so it can't carry a lot of fuel with it. Or a car for ordinary use will want to achieve higher amounts of fuel efficiency, and that is helped by thinning out the rod. So, hello, Luke. You have been brought back to the screen. That is everything we've got for you today. Thank you very much for watching Crankshaft, a group project over the module Crankshaft. Okay, thank you. Goodbye.
Bye, Jacob. Good seeing you.
Good seeing you too, Luke.